Hey everyone, and welcome. Today, we're going to peel back the curtain on something you use every single day, but probably don't think twice about: the mirror. We're going to see how just a few simple rules of physics can create the totally fascinating and sometimes pretty weird world of reflections.
So let's just jump right in with a question that I guarantee has puzzled you at the breakfast table. Why is it that when you look into the bowl of a spoon, you're upside down, but when you flip it over, you're right side up? And a regular mirror doesn't do either. Well, it's not magic, I promise you, it's physics, and we're about to break it all down. You see, to get how mirrors work, we first have to talk about the star of the show, light itself. Everything a mirror does, from a basic reflection to making things look huge, all starts with how it plays with light. And it's all governed by one beautiful, simple law.
So, what even is light? Well, think of a massive spectrum of energy out there, the electromagnetic spectrum. Light is just this tiny, tiny little slice of it that our eyes have evolved to see. We're talking about wavelengths from around 400 to 750 nanometers. This is the stuff that lets us see, well, everything.
And light moves fast. I mean, ridiculously fast. In the vacuum of space, it's zipping along at 300 million meters per second. That's the universe's ultimate speed limit. Nothing goes faster. It's why when you glance at a mirror, the reflection feels instant. The light from you hits the mirror and bounces back to your eye in basically no time at all. Now, technically, light behaves like a wave. But for what we're doing today, understanding mirrors, we can actually simplify things a whole lot. We can just imagine light traveling in a perfectly straight line, which physicists call a ray. It's a neat little shortcut called ray optics, and it works perfectly. And here it is. This is the one. The single, simple rule that explains everything else we're about to talk about. When a ray of light hits a surface, the angle it comes in at is exactly the same as the angle it bounces off at. That's it. That one little idea explains every reflection you've ever seen, from your bathroom mirror to a crazy funhouse. Okay, so that rule is pretty straightforward for a flat surface, right? But what happens when we take that exact same rule and apply it to a surface that isn't flat at all? Let's see how things start getting really interesting when we curve the mirror. We're basically dealing with two main types of curved mirrors. First, you've got concave mirrors, which curve inward. The easy way to remember that is they look like you're looking into a cave. And then you have convex mirrors, which bulge outward towards you. Each one messes with light in its own unique way.
Now, to really get what's going on, we need a sort of roadmap for these mirrors. The very center of the mirror's surface is called the pole. The line running right through it is the principal axis. But the most important point on this whole map is the one labeled F, the focus. This is a special spot where parallel rays of light all get sent after they bounce off the mirror. That focal point is the key to, well, everything. And that focus isn't just in some random spot. Nope, there's a simple, perfect little bit of math to it. The distance from the mirror out to the focus, what we call the focal length F, is always exactly half of the mirror's radius of curvature, R. It's a clean little formula that helps us predict exactly what a reflection's going to look like. All right, so when a mirror makes an image, that image can be one of two types. It can be either real or virtual. One of them you can actually project onto a screen, like at the movies. The other is more of an optical illusion. It only exists inside your brain. Let's break that down. So here's the big difference. A real image forms where light rays actually cross paths in the real world. Think of a movie projector. It's creating a real image on the screen. These are usually flipped upside down. But a virtual image is what you see in your bathroom mirror. The light rays don't actually meet behind the glass. They just look like they're coming from back there. Your brain fills in the gaps. You can't put a screen there and see the image. And these are usually upright.
Now, this might sound like it's getting complicated, but don't worry. Physicists have this amazing toolkit that makes it super simple to figure out exactly where an image is going to show up. And the best part is, you don't need to track every single ray of light, just 2 or 3 special ones that follow very easy rules. These are our 3 secret highways for light. Rule 1. Any ray that comes in parallel to that main axis will always bounce off and go right through the focus. Rule 2. The exact opposite is also true. Any ray that goes through the focus first will bounce off and travel out parallel to the axis. And rule 3. Any ray that goes to the center of curvature just hits the mirror dead on and bounces straight back the way it came. Okay, let's watch this in action, one step at a time. Here's our first rule. You can see a ray leaving the top of the object, traveling parallel to the axis. The moment it hits the mirror, Bam! It gets redirected right through that special focal point, F.
Now let's bring in our second ray. This one also leaves the top of the object, but it aims for the focus first. And as soon as it hits the mirror, the laws of physics take over and shoot it out perfectly parallel to the axis. And look at that. Do you see where those two reflected rays cross? That's it. That's the spot. That's exactly where the top of the image is going to form. Just by following two simple, predictable paths, we can pinpoint exactly where the reflection will be and even how big it's going to be. Pretty cool, right?
Drawing these diagrams is awesome for getting a feel for things, but what if we want to be super precise and just calculate the answer? Well, for that, we have one single powerful formula that does it all.
This little thing right here is the mirror equation. And honestly, it's way more powerful than it looks. All that ray tracing we just did, all that drawing, this single elegant formula does the exact same job, but with math. It perfectly connects the object's distance, the image's distance, and the mirror's focal length. So let's quickly break down the terms. U is just how far the actual object is from the mirror. V is how far the image appears to be from the mirror. And F is that focal length we talked about, half the mirror's curve. If you know any two of these, you can always find the third.
So why do we care about any of this? Because these principles are literally everywhere you look. That side view mirror on your car, that's a convex mirror, giving you that wide view to keep you safe. A magnifying or makeup mirror, that's a concave mirror, creating a big virtual image of your face. And the huge telescopes peering into deep space, they use giant concave mirrors to gather light from stars billions of miles away. And here's a really wild effect that the math totally predicts. Have you ever watched someone running towards you in your car's side view mirror? They're moving at a constant speed, but in the mirror, it looks like they're getting faster and faster as they get closer. Their image actually appears to accelerate like crazy. That's not an illusion. That's just the physics of reflection at work.
And that brings us right back to the beginning, that spoon. It's really just two mirrors in one, isn't it? The inside is a concave mirror, and the back is a convex mirror. And now, based on everything we just went over, from that one simple law of reflection to real and virtual images, you have all the tools you need to understand exactly why one side flips you upside down. The physics isn't bending reality, it's just showing you how reality works.